Despite all our technological achievements, landing rovers on Mars, sending spacecraft to the outer edges of our solar system, peering into the depths of the universe with the most powerful telescopes ever built, we cannot leave the Milky Way. Not today, not in 100 years, perhaps not ever. And this isn't just about needing better rockets or more funding for space agencies. The barriers keeping us trapped in our galactic neighborhood are woven into the very fabric of reality itself. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. And one quick question for you. If you could instantly master any scientific field, which one would you choose? Let me know in the comments below. I'll pin the most creative answer. Now let's begin. So let's start with the basics. Let's talk about just how incomprehensibly large our galaxy actually is. When astronomers measure cosmic distances, they don't use miles or kilometers. Those units become meaningless at such scales. Instead, they use something called a light year. This is the distance that light travels in one Earth year. Now, light is the fastest thing in the universe. It blazes through the vacuum of space at approximately 186,000 miles per second. That's about 300,000 kilometers per second. In just 1 second, a beam of light could circle our entire planet nearly 7.5 times. At that incredible velocity, light covers almost 6 trillion miles in a single year. 6 trillion. That's a 6, followed by 12 zeros. To put that in perspective, if you could somehow drive a car at highway speed non-stop 24 hours a day, 7 days a week, it would take you over 11 million years to travel just 1 light year. Now, with that scale in mind, let's look at our galaxy. The Milky Way stretches approximately 100,000 light years from edge to edge. Some recent studies suggest it might be even larger, perhaps up to 200,000 light years, when you include the outer stellar halo. Our solar system sits roughly 26,000 light years from the galactic center. That means even light itself, the fastest messenger in the cosmos, takes 26,000 years to travel from our sun to the supermassive black hole lurking at the heart of our galaxy. But here's where things get really humbling. The Milky Way, as enormous as it is just one galaxy among billions. The nearest major galaxy to us is Andromeda, also known as Messier 31. It's a stunning spiral galaxy, actually larger than our own, containing roughly 1 trillion stars, and it sits approximately 2.5 million light-years away. Let me say that again. 2.5 million light-years. The light reaching your eyes when you look at Andromeda tonight started its journey before modern humans even existed. When those ancient photons began their cosmic voyage, our ancestors were still figuring out stone tools. Entire species have evolved and gone extinct in the time it took that starlight to reach Earth. And Andromeda is considered our neighbor, our close neighbor. When astronomers talk about the observable universe, they're discussing a sphere roughly 93 billion light-years in diameter. Within that unimaginable volume, we've identified over 2 trillion galaxies. 2 trillion islands of stars, each containing billions or hundreds of billions of suns, separated by gulfs of nearly empty space that dwarf our comprehension. This is the playing field we're dealing with. This is why the question of leaving our galaxy isn't just a matter of building faster rockets. Now let's dive deeper into the first major barrier standing between us and intergalactic travel, the speed of light itself. In 1905, a young patent clerk in Switzerland published a paper that would forever change our understanding of the universe. His name was Albert Einstein, and his special theory of relativity contained a revolutionary idea. The speed of light in a vacuum is absolute. It's not just very fast, it's the ultimate cosmic speed limit. Nothing carrying information or mass can ever exceed it. This wasn't just a guess or a theory waiting to be disproven. Over the past century, countless experiments have confirmed this limit. Particle accelerators like the Large Hadron Collider have pushed subatomic particles to 99.9999% the speed of light. Yet they can never quite reach it. The math is unforgiving. As any object with mass accelerates toward light speed, its relativistic mass increases. The faster you go, the heavier you become, and the more energy you need to accelerate further. To actually reach the speed of light, you would need infinite energy. And infinity isn't just a very large number, it's a mathematical impossibility. No matter how advanced our technology becomes, no matter what exotic fuels or propulsion systems we develop, this barrier appears to be fundamental to reality itself. So what does this mean for intergalactic travel? Let's be optimistic. Let's imagine humanity develops technology that allows us to travel at 99% the speed of light. This is wildly beyond anything we can currently achieve, but let's dream big. At that incredible velocity, how long would it take to reach Andromeda? About 2.5 million years. Your great-great-great-grandchildren, continuing for about 100,000 generations, would still not see the journey's end. Civilizations would rise and fall. Languages would evolve beyond recognition. The very concept of humanity might transform into something unrecognizable. And all of this is assuming everything goes perfectly. Assuming your spacecraft doesn't encounter any debris, doesn't experience any technical failures, and somehow maintains life support across geological timescales. Now, there's a fascinating twist to this story. Einstein's relativity also tells us that time behaves strangely at high velocities. The faster you move through space, the slower time passes for you relative to someone standing still. This effect, called time dilation, has been measured and confirmed countless times. If you could somehow travel at 99.9% the speed of light, something remarkable would happen. While 2.5 million years would pass on Earth, you, the traveler, might experience only about 35,000 years. Still an impossibly long journey, but significantly shorter than the external time elapsed. Push even closer to light speed, say 99.9999%, and you might experience only a few hundred years while millions of years tick by back home. But here's the profound loneliness in that scenario. Even if you could make the journey and somehow survive it, everyone and everything you ever knew would be gone. Not just dead, but ancient history, dust, forgotten. The Earth itself might look completely different. Continents would have shifted. Species would have evolved and gone extinct. Human civilization, if it still existed, would be utterly unrecognizable. You would arrive as a living fossil from an impossibly distant past, and we haven't even discussed the energy requirements yet. Let me give you some numbers that will make your head spin. The fastest human-made object ever is the Parker Solar Probe. As it swoops close to the Sun, using our star's gravity to accelerate, it reaches speeds of approximately 430,000 miles per hour. That's around 692,000 kilometers per hour. Incredibly fast by our standards. At that speed, you could travel from New York to Los Angeles in about 20 seconds. But even at that blistering pace, the Parker Solar Probe is traveling at only about 0.06% the speed of light. To reach Andromeda at that velocity would take over 4 billion years. Longer than the Earth has existed, longer than complex life has swam in our oceans. To accelerate a spacecraft of any meaningful size to even a significant fraction of light speed requires energy on a scale that's almost impossible to grasp. Let's say we wanted to send a ship about the size of the space shuttle, roughly 100,000 kilograms, to just 10% the speed of light. The kinetic energy required would be approximately 45 quadrillion joules. That's more than the total energy consumption of human civilization for an entire year, just to accelerate the ship. You'd need roughly the same amount of energy again to slow down at your destination, unless you planned to simply fly past at incredible speed. Now multiply that by roughly 1,000 to approach real relativistic velocities, and you begin to see the scale of the problem. But wait, it gets worse. The fuel problem creates a vicious cycle. To carry enough fuel to accelerate to high speeds, you need a bigger ship. But a bigger ship requires more fuel to accelerate, which makes the ship even bigger, which requires more fuel. This is called the tyranny of the rocket equation, and it's one of the fundamental challenges of space travel. Chemical rockets, the kind we use today, can only exhaust their propellant at a few kilometers per second. To reach even a small fraction of light speed, you would need to carry more fuel than exists on Earth, literally more mass in propellant than our entire planet. What about nuclear propulsion? It's better, but still not enough. Projects like the theoretical Project Orion from the 1950s and 60s proposed riding a series of nuclear explosions to achieve high velocities. Modern concepts like nuclear pulse propulsion or fusion rockets could theoretically reach perhaps 10 to 20% of light speed under optimal conditions. But even these advanced systems fall woefully short of what intergalactic travel demands. Let's push our imagination further. What about antimatter? Antimatter is the most energy-dense substance we know of. When matter and antimatter collide, they annihilate each other completely, converting 100% of their combined mass into pure energy. Compare this to nuclear fission, which converts less than 1% of mass to energy, or nuclear fusion, which manages perhaps 0.5%. Antimatter is the ultimate fuel. In theory, an antimatter propulsion system could accelerate a spacecraft to significant fractions of light speed. Some calculations suggest that with a perfect antimatter rocket, you might reach perhaps 40 to 50% of light speed. The math actually works out, at least on paper, but here's the crushing reality. Producing antimatter requires more energy than it releases. Far more. When we create antimatter in particle accelerators like those at CERN, we invest billions of times more energy than we get back. The process is staggeringly inefficient. Currently, all the antimatter humanity has ever produced amounts to mere nanograms, tiny, almost immeasurable quantities. To fuel an interstellar mission, let alone an intergalactic one, we would need tons of the stuff, and storing it presents another nightmare. Since antimatter annihilates on contact with regular matter, you'd need to suspend it in perfect magnetic bottles, completely isolated from the walls of its container, for millions of years. Even the most optimistic projections suggest that antimatter production at scale would require the energy output of entire star systems. We're talking about harnessing power on a level that would classify us as a Type 2 civilization on the Kardashev scale. A civilization capable of capturing all the energy output of its home star. We're currently not even a Type 1 civilization yet. We haven't even learned to harness all the energy available on our own planet. So the speed of light isn't just a suggestion, it's a wall, a fundamental barrier built into the architecture of space-time itself. And even approaching that wall requires energy resources that seem forever beyond our grasp. But suppose, just suppose, we could somehow solve the energy problem. Suppose we discovered some revolutionary new physics or stumbled upon a cosmic shortcut. We'd still face another barrier, one that's arguably even more insurmountable. The universe is expanding. And it's not just expanding, it's accelerating. This discovery shocked the scientific community when it was confirmed in 1998. Two independent research teams studying distant supernovae to measure the expansion rate of the universe found something nobody expected. Instead of slowing down due to gravity, as everyone assumed, cosmic expansion was speeding up. This acceleration is driven by something we call dark energy, And I want to be honest with you about something. We don't really know what dark energy is. We can measure its effects, we can quantify its influence, but its fundamental nature remains one of the deepest mysteries in modern physics. It seems to be a property of space itself, a kind of anti-gravity that pushes the universe apart at ever-increasing rates. Dark energy makes up roughly 68% of the total energy content of the universe. Regular matter, the stuff you and I are made of, the stuff that makes up stars and planets and galaxies, accounts for less than 5%. The rest is dark matter, another mysterious substance we can detect only through its gravitational effects. So our universe is dominated by invisible, poorly understood forces that are actively working to push everything apart. Now here's where this gets truly mind-bending. Space itself is expanding. It's not that galaxies are flying apart through space like shrapnel from an explosion. It's that the fabric of space between them is stretching. New space is constantly being created, filling in the gaps between cosmic structures. Close to home, this expansion is negligible. The gravitational bonds holding together our solar system, our galaxy, and even our local group of galaxies are strong enough to resist the expansion. Andromeda isn't flying away from us. In fact, it's falling toward us, and our two galaxies will collide in about 4.5 billion years. But on larger scales, beyond our local gravitational neighborhood, the expansion dominates, and the farther away something is, the faster it appears to recede. This relationship is described by Hubble's law, named after Edwin Hubble, who first observed the expansion of the universe in 1929. The current expansion rate, called the Hubble constant, is approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. What does that mean in practical terms? It means that for every megaparsec of distance between us and a distant object, that object appears to be moving away from us at about 70 kilometers per second. An object 2 megaparsecs away recedes at 140 kilometers per second. 3 megaparsecs, 210 kilometers per second, and so on. At a certain distance, this recession velocity exceeds the speed of light. Wait, I hear you saying, didn't you just tell me nothing can travel faster than light? How can distant galaxies be moving away from us at superluminal speeds? Here's the key insight. The galaxies themselves aren't moving through space faster than light. Space itself is expanding between us, and there's no speed limit on the expansion of space. Einstein's speed limit applies to objects moving through space, not to space itself stretching. The distance at which recession velocity equals light speed is called the Hubble radius, currently about 14 billion light-years away. Objects beyond this distance are receding from us faster than light. We can still see some of them because their light started traveling toward us long ago, when they were closer. But any light they emit now will never reach us. They've passed beyond our cosmic event horizon, and here's the truly devastating implication for intergalactic travel. Because the expansion is accelerating, this horizon is effectively shrinking. More and more of the universe is passing beyond our reach forever. Let me paint this picture more vividly. Right now, we can observe roughly 2 trillion galaxies in the visible universe. But we could never visit most of them, even with unlimited technology and infinite time. They're already beyond our reach. Even traveling at the speed of light, we could never catch up to them because the space between us is expanding faster than light could cross it. And it's getting worse. As the universe continues to accelerate, more galaxies will slip beyond this cosmic horizon. Current models suggest that in roughly 100 billion years, observers in our galaxy won't be able to see any other galaxies at all. The universe will appear to contain only our local group, a lonely island in an apparently empty void. Future astronomers, if any exist by then, might have no way of knowing that other galaxies ever existed. The evidence will have literally disappeared over the edge of the observable universe. This is one of the most haunting implications of modern cosmology. The universe is not only vast beyond comprehension, it's actively erasing evidence of its own vastness. The cosmic story is being hidden from future generations. But let's bring this back to our central question: can we leave the Milky Way? Given the expansion of space, our realistic targets are limited to what astronomers call the local group. This is a collection of more than 80 galaxies bound together by mutual gravitational attraction. The largest members are Andromeda and the Milky Way. Others include the Triangulum galaxy, also called Messier 33, and numerous smaller dwarf galaxies like the Large and Small Magellanic Clouds. The local group spans roughly 10 million light-years. Everything within this group is gravitationally bound, meaning expansion won't carry these galaxies away from each other. In fact, Andromeda is approaching us at about 250 kilometers per second, drawn by mutual gravity. We're destined to merge. So in theory, the local group represents our cosmic neighborhood, our ultimate reach. If we could somehow develop technology to travel between galaxies, these roughly 80 galaxies might be accessible. Beyond them, the accelerating expansion creates an ever-widening gulf that even light cannot cross. But even reaching Andromeda presents challenges that border on the impossible: 2.5 million light-years. Let's break down what that actually means for a hypothetical mission. First, consider navigation. Space is not empty. It's permeated by gas, dust, and radiation. The interstellar medium within our galaxy contains roughly 1 atom per cubic centimeter on average. That might sound like nothing, but at relativistic speeds, even sparse matter becomes deadly. At 50% the speed of light, a grain of dust would strike your spacecraft with the energy of a small bomb. Larger particles would be catastrophic. And you'd be traveling through this gauntlet for millions of years. Then there's intergalactic space, the void between galaxies. It's even emptier than interstellar space, with perhaps 1 atom per cubic meter. But it's also bathed in high-energy cosmic rays and gamma radiation. Any spacecraft would need shielding on a scale we can barely imagine. And this brings us to another fundamental problem: the spacecraft itself. No human-made object has ever been designed to function for more than a few decades. Our longest-running space missions, the Voyager probes, have been operating for about 46 years, as of 2023. They're remarkable achievements, true testaments to engineering brilliance, but they're also showing their age. Systems are failing, power is dwindling. Within the next decade or so, they'll go silent forever. Now imagine building something that needs to function reliably for millions of years. Every mechanical system degrades over time. Metals fatigue, circuits corrode, radiation damages electronics. Even in the cold vacuum of space, entropy takes its toll. The longest-lasting human artifacts on Earth, things like Stonehenge or the pyramids, are only thousands of years old and have required significant natural protection to survive even that long. No material we know of can withstand millions of years of operation without maintenance, and maintaining a spacecraft across intergalactic distances presents its own impossible challenges. You can't send repair crews, you can't transmit instructions, since radio signals would take millions of years to arrive. Any intergalactic vessel would need to be completely self-sufficient, self-repairing, self-maintaining, effectively immortal. It would need to carry not just fuel, but the ability to manufacture replacement parts, repair systems, and perhaps even rebuild itself entirely over the course of the journey. Some scientists have proposed that biological systems might actually be more suitable for such journeys. Life has a built-in repair mechanism through reproduction. A colony of microorganisms or even complex life could potentially perpetuate itself indefinitely, with each generation being a fresh copy. Perhaps intergalactic travelers wouldn't be machines at all. Perhaps they would be living ecosystems, tiny biospheres hurtling through the void. But this raises profound questions about what we mean by travel. If the organisms that arrive at Andromeda are separated from those that departed by millions of generations, have they really traveled? Or has something new been created at the destination? The Ship of Theseus problem takes on cosmic proportions. And we haven't even discussed the biological challenges facing any hypothetical human travelers. The human body evolved on Earth, in Earth's gravity, protected by Earth's magnetic field, exposed to Earth's day-night cycles. Take us away from these conditions, and we begin to break down in alarming ways. Astronauts on the International Space Station, after just 6 months in microgravity, experience significant bone density loss. Their muscles atrophy, their cardiovascular systems weaken. Their eyes change shape, sometimes causing permanent vision problems. Fluid shifts in microgravity cause increased pressure in the skull. The immune system becomes confused. Even their gut bacteria undergo changes. We've developed countermeasures for some of these issues: exercise regimens, medications, specialized diets, but we've never tested human biology beyond low Earth orbit for extended periods. The longest single spaceflight was Valery Polyakov's 437 days aboard the Mir station. He suffered significant physical effects but ultimately recovered after returning to Earth. Now imagine no return to Earth. Imagine generations living entirely in artificial environments. Imagine millions of years of isolation from everything our biology expects. Some researchers believe humans could adapt, that over many generations, natural selection would modify our descendants to thrive in space. They would become something new, something evolved for cosmic travel, but they would no longer be human, not in the sense we understand that word. Others propose more radical solutions. Perhaps we could upload human consciousness into machine substrates, digital minds that could survive indefinitely, unconstrained by biological frailty. Or perhaps we could merge biology and technology, creating cyborg beings that combine the best of both worlds. These ideas venture into philosophy as much as science. Would a digital copy of your mind actually be you? Would it have consciousness, experiences, a sense of self? Or would it just be an extremely sophisticated computer program that mimics these qualities? We don't know. We don't even have a scientific definition of consciousness, let alone a way to transfer it. The challenges of intergalactic travel, it seems, lead us inevitably toward the deepest questions about what it means to be human, what it means to be alive, what it means to exist. Perhaps that's one of the hidden gifts in these seemingly frustrating limitations. They force us to confront who we are, to define what we value, to ask whether we would still recognize ourselves after the transformation such a journey would require. Let's take a moment to appreciate something profound. Everything we've discussed so far, the speed of light limitation, the tyranny of the rocket equation, the expansion of space, these aren't just engineering problems waiting for clever solutions. They appear to be fundamental features of reality itself. This is a crucial distinction. Throughout human history, we've overcome countless barriers that once seemed insurmountable. We learned to fly when experts declared it impossible. We split the atom. We walked on the moon. We connected billions of minds through a global information network. Time and time again, human ingenuity has triumphed over apparent limitations. But there's a difference between technological limitations and physical laws. Technological limitations are about not knowing how to do something yet. We didn't know how to fly until we understood aerodynamics. We didn't know how to cure smallpox until we developed vaccines. These were knowledge gaps waiting to be filled. Physical laws are different. They describe what the universe permits, and the speed of light appears to be one of these fundamental permissions, not a technological barrier, but a cosmic boundary written into the equations that govern everything. Now, some might argue that our understanding of physics is incomplete. And they're absolutely right. We know our current theories are imperfect. General relativity and quantum mechanics, the two pillars of modern physics, contradict each other in important ways. A theory of quantum gravity which would unite them remains elusive. Perhaps some future breakthrough will reveal loopholes we can't currently imagine. Perhaps the speed of light limit can somehow be circumvented without violating the underlying principles of relativity. It's important to remain humble about what we don't know, but it's equally important to be honest about what we do know. And what we know, based on over a century of experimental confirmation, is that the speed of light limit is incredibly robust. Every experiment designed to find violations has failed. Every attempt to push particles past this barrier has confirmed it. The evidence is overwhelming, so while we should stay curious and open-minded, we should also be realistic. Planning for intergalactic travel based on hoped-for physics breakthroughs is like planning your retirement based on winning the lottery. It might happen, but it's not a sound strategy. Let's explore some of the theoretical concepts that science fiction loves to invoke. You've probably heard of them. Wormholes, warp drives, faster-than-light travel through exotic physics. Are any of these actually possible? Wormholes, also called Einstein-Rosen bridges, are theoretical tunnels through space-time. They emerge from the mathematics of general relativity. If they existed, they could potentially connect distant points in space, allowing nearly instantaneous travel between them. Step into one end and emerge at the other, millions of light-years away, without crossing the intervening space. It sounds perfect. Too perfect, perhaps. Here's the problem. While wormholes are mathematically possible in general relativity, actually creating or maintaining one would require exotic matter with negative energy density. This is matter that gravitationally repels rather than attracts. And while quantum mechanics hints that such matter might exist in tiny amounts, generating enough to stabilize a traversable wormhole seems far beyond any realistic capability. Moreover, even if you could somehow create a stable wormhole, you'd face the causality problem. Because wormholes could potentially allow faster-than-light travel, they could theoretically be used to violate cause and effect. You could, in principle, travel back in time and create paradoxes. Many physicists believe the universe has built-in mechanisms to prevent such paradoxes, mechanisms that would automatically destabilize any wormhole before it could be used for such purposes. Stephen Hawking called this the chronology protection conjecture. The universe, it seems, protects itself from time travel paradoxes. Whether this conjecture is correct remains unknown, but it suggests that wormholes might be inherently unstable or impossible to use for practical travel. What about warp drives? In 1994, physicist Miguel Alcubierre proposed a fascinating concept. Instead of moving a spacecraft through space at faster-than-light speeds, which relativity forbids, why not move space itself around the spacecraft? Contract space in front of the vessel, expand it behind, and the ship rides a wave of space-time toward its destination. From inside the bubble, you're not moving at all. Space is moving around you. The Alcubierre drive is mathematically consistent with general relativity. It doesn't technically violate the light speed limit because the ship itself never exceeds it. Only the space-time bubble moves superluminally. But like wormholes, the Alcubierre drive requires exotic matter, vast amounts of it. Original calculations suggested you'd need more negative energy than the total mass energy of the observable universe. Later refinements have reduced this requirement somewhat, but it remains utterly beyond any foreseeable technology. There's also a troubling issue at the destination. When the warp bubble decelerates, all the high-energy particles accumulated on its leading edge would be released in a devastating blast. You might arrive at your destination only to sterilize it with radiation. And here's something subtle but important. To create an Alcubierre warp bubble, you would need to arrange exotic matter in a very specific configuration ahead of your intended path. But how do you send that exotic matter ahead of you faster than light to set up the bubble? You face a chicken and egg problem. You need a warp drive to build a warp drive. Some recent research has explored variations on the Alcubierre concept that might require less exotic matter, or perhaps positive energy under certain conditions. In 2021, physicist Eric Lentz published a paper suggesting that certain warp configurations might work with purely positive energy. But these ideas remain highly speculative, and many physicists are skeptical. The honest assessment is this: wormholes and warp drives are wonderful concepts for science fiction. They might even represent real possibilities in some ultimate theory of physics we haven't discovered yet. But based on our current understanding, they're not technologies we can plan around, they're dreams, not roadmaps. This might seem discouraging, but I want to offer a different perspective. The limitations we're discovering aren't arbitrary restrictions imposed by a stingy universe. They're features of a cosmos that operates by consistent, comprehensible rules. Rules we can study, understand, and appreciate. Rules that make science possible in the first place. If the laws of physics were different, if faster-than-light travel were trivially easy, we might not exist to contemplate the question. The same physics that constrains our travel also enables the stability of atoms, the burning of stars, the formation of planets, and the evolution of life. We are products of these laws, not prisoners of them. And there's something profound in that recognition. We are the universe becoming aware of itself. We are stardust contemplating the stars. The very atoms in your body were forged in the nuclear furnaces of ancient suns that exploded billions of years ago, scattering their enriched material across space to eventually coalesce into new solar systems, new planets, and eventually you. Speaking of our cosmic insignificance and grandeur, if you enjoyed this exploration of our universal boundaries, you might want to check out my other video about just how incredibly small we are within the Milky Way itself. It really puts things in perspective when you realize that even within our own galaxy, we occupy a tiny, almost invisible corner of a vast cosmic structure. Sometimes understanding how small we are makes us appreciate how remarkable it is that we exist at all. Now let's talk about something that might offer a glimmer of hope amidst all these limitations. What if we're asking the wrong question? What if the goal shouldn't be physically transporting humans to other galaxies, but rather extending our presence and knowledge in other ways? Consider information. Information can travel at the speed of light. We already send radio signals, laser pulses, and other electromagnetic radiation across vast distances. These signals carry our presence, our thoughts, our culture into the cosmos. In 1974, the Arecibo radio telescope transmitted a message toward the globular star cluster Messier 13, about 25,000 light-years away. The message contained basic information about humanity, our solar system, our DNA structure, and our place in the galaxy. It was a symbolic gesture, a cosmic hello, but it demonstrated that we can project ourselves across interstellar distances at light speed. Of course, Messier 13 is within our galaxy. Reaching Andromeda with a radio signal would take 2.5 million years, and any response would take equally long to return. A 5 million year round trip for a simple conversation. Not exactly practical communication. But perhaps communication isn't the only option. What about sending machines? Robotic probes don't need life support. They don't get bored or lonely. They don't experience the psychological strain of million-year journeys. With sufficient autonomy and self-repair capabilities, machines might be our best ambassadors to the cosmos. The concept of self-replicating probes, often called von Neumann probes, after mathematician John von Neumann, takes this idea further. Imagine a probe that arrives at a distant star system, mines local resources, and builds copies of itself. Those copies then travel to other star systems and repeat the process. Through exponential growth, such probes could theoretically spread across an entire galaxy in just a few million years, even at relatively slow speeds. This concept suggests something intriguing. If intelligent civilizations commonly arise in galaxies, and if they develop self-replicating probe technology, the galaxy should be filled with such probes by now. The fact that we haven't detected any is one formulation of the famous Fermi paradox, the question of why we see no evidence of extraterrestrial intelligence despite the apparent probability that it should exist. Perhaps intelligent life is far rarer than we assume. Perhaps civilizations destroy themselves before developing such technology. Perhaps they exist but choose not to expand. Perhaps they're here and we haven't recognized them. The possibilities are numerous and none are fully satisfying. But let's focus on what self-replicating probes might mean for intergalactic travel. Could we send such machines to Andromeda? The distances are daunting, but perhaps not impossible. At 1% the speed of light, achievable with advanced nuclear propulsion, the journey would take about 250 million years. That's a long time, but it's shorter than many geological epochs on Earth. Dinosaurs roamed our planet more recently than that. A truly autonomous, self-repairing von Neumann probe might survive such a journey. Upon arrival, it could explore, catalogue, and report back, though its reports would take another 2.5 million years to reach us. The civilization that receives those reports might be utterly different from the one that sent the probe. This raises fascinating questions about purpose and meaning. Why would we send a probe whose findings we'd never live to see? Why invest resources in a project that would benefit only our incredibly distant descendants, if they even still exist? Perhaps because we're human. Perhaps because curiosity and the drive to explore are fundamental to our nature. Perhaps because we want to believe that something of us, some echo of our existence, will persist across cosmic time. Or perhaps we might find other motivations. Perhaps the process of building such a probe would benefit us in ways beyond its eventual mission. Perhaps the technologies developed would have more immediate applications. Perhaps the act of reaching toward infinity gives meaning to our finite lives. Let me tell you about a real project that embodies this spirit, Breakthrough Starshot. Announced in 2016, Breakthrough Starshot is a research and engineering initiative funded by billionaire Yuri Milner and supported by scientists including the late Stephen Hawking. Its goal is audacious yet potentially achievable. Send tiny spacecraft to our nearest stellar neighbor, the Alpha Centauri system, within a generation. The approach is radical. Instead of sending a massive spacecraft, Starshot proposes using thousands of gram-scale probes called star chips. These would be thin, lightweight wafers carrying cameras, sensors, and communication equipment. Attached to each chip would be a light sail, a reflective surface several meters across but weighing almost nothing. Powerful ground-based lasers would illuminate these sails with concentrated light. The radiation pressure would accelerate the probes to approximately 20% the speed of light within minutes. At that velocity, they would reach Alpha Centauri in about 20 years. 20 years. Within a human lifetime. The probes would fly through the Alpha Centauri system, capturing images and data, then beam their findings back to Earth using tiny onboard lasers. Even at light speed, the return signal would take over 4 years, but we might have our first close-up views of another star system within about 25 years of launch. Now Breakthrough Starshot faces enormous technical challenges. The lasers required would need to be more powerful than anything currently built. The sails would need to be incredibly reflective and heat-resistant. The chips would need to survive intense acceleration and decades of cosmic radiation. Communication across 4 light-years with a gram-scale transmitter is extremely difficult, but none of these challenges violate physics. They're hard engineering problems, not fundamental impossibilities. And progress is being made. If Breakthrough Starshot succeeds, it would represent humanity's first interstellar mission. A probe that travels beyond our solar system to another star, not quite intergalactic travel, but a beginning, a proof of concept, a statement that we can reach beyond our cosmic cradle. Could similar technology be scaled up for intergalactic distances? Theoretically, perhaps, but the challenges multiply enormously. Accelerating probes to 20% light speed requires enormous power over short distances because you can only push them while they're close enough for the lasers to focus effectively. For longer journeys, you'd need relay stations, lasers positioned along the route to provide additional acceleration. But how do you build relay stations in intergalactic space? Communication becomes even more problematic. A gram-scale probe trying to send data from Andromeda would need to transmit across 2.5 million light-years. The signal would be unimaginably faint by arrival. You'd need receivers of staggering sensitivity or probes with much more powerful transmitters, which would make them heavier, which would require more power to accelerate. Every solution creates new problems. Every breakthrough reveals new barriers. Yet this is the nature of science and exploration. We push against limits, expand our understanding, and sometimes find ways through obstacles that once seemed insurmountable. A century ago, even reaching the moon was considered impossible by serious scientists. Now we're planning permanent lunar bases. Perhaps a century from now, interstellar travel will be routine. Perhaps a millennium from now, we'll have techniques we can't currently imagine. Perhaps in a million years, our descendants will look back at our concerns about intergalactic travel the way we look back at medieval fears about sailing off the edge of the Earth. Or perhaps not. Perhaps some limits really are absolute. Perhaps the universe has placed certain destinations permanently beyond reach. Either way, the journey of discovery is worthwhile. The questions we ask shape who we become. The challenges we face reveal our character and our capabilities. Let's continue exploring these challenges. Let's talk about time and how it becomes perhaps our most formidable enemy in any discussion of intergalactic travel. Time is something we rarely think about deeply. It flows around us, through us, carrying us from moment to moment like a river we cannot escape. We measure it in heartbeats and breaths, in sunrises and seasons, in birthdays and anniversaries. Our entire civilization is built around its rhythm. But when we contemplate intergalactic travel, time transforms from a familiar companion into an incomprehensible adversary. Let's ground this in something tangible. The oldest human structures still standing are roughly 5,000 years old. The Great Pyramid of Giza was built around 2500 BCE. Stonehenge dates to approximately 3000 BCE. These monuments have survived wars, earthquakes, climate changes, and the rise and fall of countless civilizations. 5,000 years seems ancient to us. It spans the entirety of recorded human history. Every empire, every religion, every scientific discovery, every work of art we consider part of our heritage fits within this window. Now consider this. The journey to Andromeda at 1% the speed of light would take 250 million years. That's 50,000 times longer than all of recorded human history. 50,000 times the span from the first Egyptian hieroglyphics to your smartphone. At 10% light speed, a more optimistic but still incredibly challenging velocity, the journey would take 25 million years. Still 5,000 times longer than human civilization has existed. Even at a relativistic 90% of light speed, requiring energy beyond our wildest current capabilities, the journey would take roughly 2.8 million years from the perspective of observers on Earth. The travelers themselves, experiencing time dilation, might only endure a few 100,000 years. Only. As if that were a short coffee break. These numbers are so large they become meaningless. Our brains evolve to comprehend timescales relevant to human life. Days, years, generations, maybe a few centuries if we're being ambitious. Our neurons simply cannot grasp what a million years means, let alone hundreds of millions. Let me try to make this visceral. Imagine every second of your life stretched out as a single grain of sand. Every heartbeat, every breath, every moment of joy and sorrow and boredom, each represented by one tiny grain. A typical human lifespan of 80 years contains roughly 2.5 billion seconds. That many grains of sand would fill a large room. Now imagine the sand representing 250 million years. You would need enough sand to bury entire mountain ranges, to fill valleys that stretch beyond the horizon. The difference between a human lifetime and an intergalactic journey isn't just quantitative, it's a completely different category of existence. During that time, everything would change, not just human civilization, but the Earth itself. Continental drift moves land masses at roughly 2 to 5 centimeters per year. Over 250 million years, that's between 5,000 and 12,000 kilometers, continents would have merged and separated, new oceans would have opened, mountain ranges would have risen and eroded away. The last time Earth looked completely different was during the Permian period, about 250 million years ago. All the continents were joined into the supercontinent Pangaea. Reptiles were just beginning to dominate. The greatest mass extinction in Earth's history was about to occur, wiping out roughly 90% of all species. If you left for Andromeda today and could somehow return, the Earth you'd find would be geologically unrecognizable. Whatever life existed would have evolved into forms we cannot predict. Humanity, if any descendants survived at all, would be something utterly alien to our understanding. This isn't speculation. This is what happens over geological time. Species evolve, continents move, stars themselves change. Speaking of stars, our own sun won't last forever. It's currently about 4.5 billion years old, roughly middle-aged for a star of its type. In another 5 billion years or so, it will exhaust the hydrogen in its core and begin to expand into a red giant, eventually engulfing Mercury, Venus, and possibly Earth. Long before that, perhaps in 1 billion years or less, the sun's increasing luminosity will make Earth uninhabitable. The oceans will boil, the atmosphere will be stripped away, life as we know it will be impossible. So any journey lasting hundreds of millions of years isn't just a voyage through space, it's a voyage beyond the lifespan of our home planet, beyond the era when the sun could support life. The travelers would be leaving not just their birthplace, but their entire stellar era. This brings us to something called deep time, a concept that geologists and cosmologists grapple with regularly. Deep time is the vast expanse of the past and future, measured in millions and billions of years. It's the temporal scale of planets, stars, and galaxies. Humans have only recently begun to comprehend deep time. For most of history, people believed the Earth was young, perhaps 6,000 years old, based on biblical genealogies. It wasn't until the 19th century that geologists began to understand that our planet was immensely older. Darwin's theory of evolution required vast stretches of time for natural selection to work. The discovery of radioactivity in the early 20th century finally gave scientists tools to accurately date rocks and fossils, revealing a 4.5 billion year history. Even now, with all our scientific knowledge, deep time remains difficult to truly internalize. We can say the numbers, but feeling their meaning is another matter entirely. Consider your own ancestors. You know your parents. You might have known your grandparents. Perhaps you've heard stories of great-grandparents. Beyond that, family history becomes hazy for most people. Go back just 10 generations, about 250 years, and you have over 1,000 direct ancestors. Go back 20 generations and you have over 1 million. Now go back 40,000 years, roughly the time since anatomically modern humans began creating art and complex tools. That's about 1,600 generations, 1,600 layers of parents and children, each living their entire lives, loving and struggling and dying, leading eventually to you. That immense chain of ancestors spans less than an eye blink in the timescales we're discussing. The journey to Andromeda would take 6,000 times longer than all of human existence. What would remain of us after such a journey? This question cuts to the heart of identity and continuity. If a spacecraft left Earth today carrying human passengers, and those passengers had children, who had children, who had children, continuing for millions of generations, would the beings who arrived at Andromeda be human? Would they be us? Consider how much humans have changed in just the last 100,000 years. Our ancestors who left Africa were anatomically similar to us, but culturally almost unrecognizable. They had no written language, no metal tools, no agriculture. Their lives were utterly different from ours. Now multiply that change by a factor of thousands. Evolution doesn't stop because you're in a spacecraft. Environmental pressures, genetic drift, perhaps intentional modification, all would shape the travelers over countless generations. They might adapt to microgravity, developing longer limbs and weaker bones. They might adapt to radiation, developing enhanced DNA repair mechanisms. They might evolve new senses, new cognitive abilities, new forms of communication. By the time they arrived at Andromeda, they might not recognize the creatures who departed. They might not even have records or memories of Earth. Millions of years is enough time for languages to transform beyond recognition, for cultures to rise and fall countless times, for the very purpose of the journey to be forgotten and replaced with something new. Some philosophers argue this doesn't matter. What counts is continuity, the unbroken chain linking the original travelers to the final arrivals. Like a river that changes every water molecule over time yet remains the same river, perhaps identity can persist through total replacement of its components. Others disagree. They argue that without memory, without cultural continuity, without recognizable connection to the original beings, you don't have travel at all, you have replacement. The original humans die and something else eventually exists in Andromeda. Calling it the same mission seems like a semantic trick. This debate becomes even more complex when you consider non-biological options. What if, instead of sending biological humans, we sent digital minds? Consciousness uploaded into computer substrates that could potentially last indefinitely. Such minds could be backed up and restored, copied and transmitted, paused and restarted. They would be immune to the biological limitations that make million-year journeys impossible for flesh and blood. But would uploaded minds truly be conscious? Would they experience the journey or merely process data about it? Would a digital copy of you actually be you, or just a very convincing simulation? We don't know. We don't even have a scientific definition of consciousness, let alone an understanding of what creates it. The hard problem of consciousness, explaining why subjective experience exists at all, remains one of the deepest mysteries in science and philosophy. Some researchers, like philosopher David Chalmers, argue that consciousness might be a fundamental feature of reality, not something that emerges from computation alone. If that's true, copying the information pattern of a brain might not copy the conscious experience. You'd create a philosophical zombie, something that behaves exactly like a conscious being, but has no inner experience. Others, like cognitive scientist Daniel Dennett, argue that consciousness is entirely a product of information processing. If you perfectly replicate the computational structure of a brain, consciousness comes along automatically. On this view, digital minds would be truly conscious, truly experiencing their existence. The stakes for intergalactic travel are enormous. If digital minds are truly conscious, uploading might offer a path to the stars. If not, we'd just be sending sophisticated robots with no more inner life than a calculator. There's another possibility that some find equally compelling and disturbing. What if consciousness isn't something you either have or don't have? What if it comes in degrees? What if a digital mind might be partially conscious, experiencing some diminished or altered form of awareness? This opens uncomfortable questions about the ethics of creating such beings. Would it be acceptable to send a partially conscious mind on a million-year journey? What if it experienced a muted form of suffering or loneliness? What moral obligations would we have toward our digital descendants? These questions might seem abstract and philosophical, but they become intensely practical when you're actually planning missions that span millions of years. Every assumption about mind, identity, and experience has concrete implications for how we should proceed. Let me share another perspective on time that might offer some strange comfort. From the viewpoint of physics, time isn't quite what our intuition tells us. Einstein showed that time is relative. It passes differently depending on your velocity and your proximity to massive objects. Two observers moving differently through space will disagree about the order of distant events, about how much time has passed, about what constitutes now. Some physicists, following Einstein's lead, embrace what's called the block universe view. In this perspective, past, present, and future all exist equally. The universe is a four-dimensional block of space-time, and what we experience as the flow of time is somewhat illusory, a feature of consciousness rather than reality. If the block universe view is correct, then in some sense, every moment exists eternally. The you who is reading these words exists forever in the space-time block. The you who was born exists forever. The you who will die exists forever. Time doesn't really flow, we just experience it that way. I'm not saying this view is certainly correct. It's controversial among philosophers and physicists, but it offers an interesting reframe. If all moments exist eternally, then perhaps the vast stretches of time separating us from intergalactic destinations are less of a barrier than they appear. Perhaps it's not about reaching across time, but about different parts of the eternal block universe being connected in different ways. This is admittedly abstract and might not provide much practical comfort. We still experience time flowing. We still live finite lives. The subjective reality of time's passage shapes everything about human existence, but sometimes when contemplating the cosmic scale, a shift in perspective helps. Sometimes the questions are more valuable than the answers. Let's ground ourselves again with something more tangible. Let's talk about what would actually happen to a spacecraft on a million-year journey. When engineers design spacecraft today, they plan for missions lasting years, perhaps decades, at the absolute maximum. The Voyager probes, launched in 1977, represent our longest-running space missions. After more than 4.5 decades of continuous operation, they're still transmitting data from the outer reaches of our solar system. This is a remarkable engineering achievement, a testament to the brilliance of the teams who built them. But even Voyager is showing its age. The plutonium power sources that generate electricity are decaying. Power output drops by about 4 watts every year. Systems have been progressively shut down to conserve energy. The heaters that keep instruments from freezing have been turned off one by one. Within the next few years, likely before 2030, Voyager will fall silent forever. 46 years. That's how long our most durable spacecraft has lasted. Now contemplate building something that needs to function for 250 million years. Not just function, but maintain itself, navigate accurately, and preserve whatever it's carrying across spans of time that dwarf the age of complex life on Earth. The challenges begin at the atomic level. Every material degrades over time. Metals corrode, even in the vacuum of space. Cosmic radiation bombards surfaces, displacing atoms, creating defects in crystal structures, gradually weakening materials from within. Polymers break down, lubricants evaporate or become gummy, seals fail, connections loosen. In laboratories, we test materials for durability using accelerated aging techniques. We expose samples to intense radiation, extreme temperatures, corrosive chemicals. We try to simulate years of wear in days or weeks, but no accelerated test can truly replicate millions of years of exposure. The long-term behavior of materials over such timescales is largely unknown because nothing we've created has ever needed to last that long. Consider something as simple as metal fatigue. When metals are stressed repeatedly, tiny cracks develop. Over time, these cracks grow. Eventually, they cause catastrophic failure. It's why aircraft are retired after a certain number of flight cycles, why bridges need regular inspection. The process happens slowly, imperceptibly, until suddenly it doesn't. A spacecraft traveling for millions of years would experience countless thermal cycles as it rotated relative to distant stars, warming slightly on one side, cooling on the other. It would encounter vibrations from onboard systems, however minimal. It would flex and shift as it accelerated, decelerated, or changed course. Each cycle would add infinitesimally to the stress accumulation. We have no materials certified for 1 million years of such treatment. We have no way to test them. We're operating completely beyond our engineering experience. Radiation presents another relentless enemy. Space is bathed in high-energy particles from various sources. The Sun emits a constant stream of charged particles called the solar wind. Beyond the solar system, galactic cosmic rays zip through the void at nearly the speed of light. These are mostly protons and atomic nuclei accelerated by supernova explosions and other violent events. Within our galaxy, the flux of cosmic rays is reasonably constant, but intergalactic space has its own radiation environment. While generally less intense than the galactic plane, it's still present, and over millions of years, even low levels of radiation accumulate to devastating doses. Electronic components are particularly vulnerable. Radiation can flip bits in computer memory, causing software errors. It can damage transistors, degrading performance over time. It can create short circuits or open circuits in delicate integrated chips. Modern electronics are already sensitive to radiation, which is why spacecraft use specially hardened components. But radiation hardening only reduces vulnerability. It doesn't eliminate it. Given enough exposure, even the most robust electronics will fail, and the doses accumulated over intergalactic timescales would be enormous. Biological systems face similar problems. DNA is damaged by radiation, leading to mutations, cancer, and cell death. Living organisms have repair mechanisms, but these aren't perfect. Accumulated genetic damage over millions of years would be catastrophic. Any biological payload, whether humans, animals, plants, or microorganisms, would need extraordinary shielding. How much shielding? The most effective radiation blockers are dense materials like lead, tungsten, or water. But effective shielding adds tremendous mass. And mass is the enemy of any space mission because more mass requires more energy to accelerate. Some calculations suggest that adequately shielding a human habitat for an intergalactic journey would require meters of dense material surrounding the living space. The resulting spacecraft would be enormously massive, requiring proportionally enormous amounts of energy to accelerate. The engineering challenges compound exponentially. Now let's consider what's actually out there in intergalactic space. What would a spacecraft encounter during its millions of years between galaxies? Surprisingly, intergalactic space isn't completely empty, it's just incredibly sparse. Within our galaxy, the interstellar medium contains roughly 1 atom per cubic centimeter on average. This is far emptier than any vacuum we can create on Earth, but it adds up over interstellar distances. A spacecraft traveling through the galaxy would encounter a steady stream of these atoms, mostly hydrogen. At low speeds, this isn't a problem. At relativistic speeds, each atom becomes a tiny projectile. A hydrogen atom striking a spacecraft at 50% the speed of light carries kinetic energy equivalent to a small bullet. At 90% light speed, the energy is even higher. Multiply this by the trillions upon trillions of atoms encountered over light years of travel, and you have a significant erosion problem. Spacecraft designs for relativistic travel often include some form of shield at the front, a dense plate or magnetic field to deflect or absorb incoming particles. But these shields themselves would degrade over time, requiring replenishment or replacement. Intergalactic space is emptier still. The intergalactic medium contains perhaps 1 atom per cubic meter, roughly 1,000,000 times less dense than interstellar space. This is good news in terms of particle bombardment, but it's bad news for any propulsion system that might rely on collecting interstellar hydrogen for fuel, like the theoretical Bussard ramjet. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined a spacecraft that scooped up interstellar hydrogen using an enormous magnetic funnel, compressed it, and used it for fusion fuel. In principle, such a ship could accelerate indefinitely, limited only by the density of the medium through which it traveled. Unfortunately, more detailed analysis revealed serious problems. The drag from collecting hydrogen might exceed the thrust generated by burning it. The magnetic scoops would need to be thousands of kilometers across, and in the sparse intergalactic medium, there simply wouldn't be enough hydrogen to collect. So any spacecraft crossing between galaxies would need to carry all its fuel from the beginning. No refueling stops, no resource collection along the way. Everything needed for a millions-year journey packed aboard at departure. Beyond the sparse gas, intergalactic space contains other hazards. Rogue objects drift between galaxies ejected from their home systems by gravitational interactions. These include rogue planets, failed stars called brown dwarfs, and probably countless smaller objects like asteroids and comets. In 2017, astronomers detected the first confirmed interstellar object passing through our solar system. They named it Oumuamua, a Hawaiian word meaning scout. It was a strange, elongated object perhaps 200 meters long, tumbling end over end as it sailed past the sun and back out into the void. Since then, we've detected at least one more interstellar visitor, a comet called Borisov, in 2019. These discoveries suggest that interstellar space is peppered with wandering objects, debris from the formation and evolution of planetary systems throughout the galaxy. Intergalactic space probably contains similar wanderers, though far more sparsely distributed. The chance of collision with any particular object is vanishingly small, but over millions of years and millions of light years, even tiny probabilities accumulate. A spacecraft would need some system for detecting and avoiding obstacles. But detecting a dark, cold object in the void of intergalactic space is extraordinarily difficult. There's no sunlight to illuminate it. It emits only faint infrared radiation from its residual heat. You might not see it until it was far too late to change course. Navigation itself presents profound challenges. When you're traveling within the Milky Way, you can navigate by the stars. The positions of thousands of stars are precisely mapped. By measuring the angles between known stars, you can determine your position and orientation with high accuracy. But once you leave the galaxy, those familiar stars merge into a single fuzzy blob of light. Individual stars become indistinguishable. The constellations that guided human travelers for millennia are meaningless from outside. What could you navigate by? Other galaxies, perhaps. The positions of nearby galaxies are known. You could use them as reference points, but galaxies move too. Over millions of years, their positions shift. The Andromeda Galaxy is approaching us at about 250 kilometers per second. Other galaxies in the local group have their own motions. To navigate accurately over intergalactic distances and timescales, you would need extraordinarily precise measurements and sophisticated models of how everything is moving. Your navigation system would need to function flawlessly for millions of years, updating its calculations as the cosmic landscape slowly shifted. Pulsars offer one possible solution. These rapidly rotating neutron stars emit beams of radiation like cosmic lighthouses. Each pulsar has a unique signature, a specific rotation rate and pattern of pulses. By detecting pulsars and comparing their observed properties to a catalogue, you could determine your position quite precisely. In fact, the Pioneer and Voyager spacecraft carry plaques and records that include pulsar maps, diagrams showing the position of our Sun relative to 14 known pulsars. The idea was that any extraterrestrial civilization finding these spacecraft could use the pulsar map to locate our solar system. But pulsars slow down over time. They lose rotational energy and their pulses become less frequent. Over millions of years, the pulsars in your catalogue might change beyond recognition. Some might stop pulsing entirely. Your navigation references would become outdated. Perhaps you could carry multiple redundant systems. Perhaps you could observe and catalogue new pulsars as your old references faded. Perhaps artificial intelligence could adapt to changing conditions in ways we can't fully anticipate. But every additional system adds complexity, mass, and potential points of failure. Communication across intergalactic distances is another formidable obstacle. Radio waves travel at the speed of light. A message sent from Andromeda would take 2.5 million years to reach Earth. Any response would take equally long to return. A simple back-and-forth exchange would span 5 million years. This isn't communication in any meaningful human sense. By the time a response arrived, the original senders would be long dead. Their civilization might have risen and fallen. The language of the message might be as incomprehensible to the receivers as linear A is to us today. But even transmitting a one-way message across such distances is enormously challenging. Radio signals spread out as they travel, following the inverse square law. Double the distance and the signal strength drops to 1/4. At intergalactic distances, the signal from any reasonably sized transmitter would be inconceivably faint by arrival. Consider the Deep Space Network, NASA's array of large radio antennas used to communicate with distant spacecraft. These antennas, up to 70 meters in diameter, can detect the faint whispers from Voyager at the edge of our solar system, roughly 22 billion kilometers away. Andromeda is about 100 million times more distant than Voyager. The signal would be 10 quadrillion times weaker. To detect it, you would need antennas millions of times more sensitive than anything we have today, or transmitters millions of times more powerful than anything we could currently build. Laser communication offers some advantages. Lasers can focus light into tight beams that spread out much less than radio waves, but even lasers diverge over intergalactic distances. And keeping a laser precisely aimed at a target 2.5 million light-years away, while both you and the target are moving, is an almost inconceivable feat of precision. Perhaps the answer is not to communicate at all. Perhaps intergalactic probes would be fully autonomous, carrying out their missions without any guidance from home. They would need to make all their own decisions, adapting to whatever conditions they encountered. This leads us toward a vision of artificial intelligence operating independently across cosmic timescales. Minds, or something like minds, making choices without any human oversight for millions of years. They would effectively become new forms of life, new civilizations, evolving and changing far from any human influence. Would they still serve human purposes? Would they remember their origins? Would they care about the species that created them? These questions venture beyond engineering into philosophy and even theology. What responsibilities do we have to the minds we create? What purposes would justify sending intelligence into the void? What would it mean for such intelligence to find meaning in its existence? Perhaps these questions reveal something important. Intergalactic travel isn't just a technical problem, it's a profound challenge to our understanding of ourselves, our place in the cosmos, and the meaning of existence across deep time. Let's pause on that thought and explore a different dimension of this challenge. Let's talk about energy and why the power requirements for intergalactic travel exceed anything our civilization could currently comprehend. Energy is the currency of the cosmos. Every action, every movement, every transformation requires it. Stars burn hydrogen to produce it. Life consumes food to extract it. Civilizations harness it in ever-increasing quantities to power their growth and ambitions. When we talk about intergalactic travel, we're talking about energy on a scale that makes our current capabilities look like striking a match to illuminate the sun. Let's start with something familiar. Your body, sitting there reading or listening to these words, consumes roughly 2,000 calories per day. That's about 8.4 million joules of energy. It powers your heartbeat, your breathing, your thoughts, the movements of your eyes across this screen. Now consider the total energy consumption of human civilization. In 2022, humanity used approximately 580 exajoules of energy. That's 580 followed by 18 zeros in joules. It sounds enormous, and it is. It represents the combined output of every power plant, every engine, every fire, every solar panel on Earth. But compared to cosmic energy scales, it's almost nothing. Our sun outputs roughly 3.8 times 10 to the 26th watts of power. Every second, it releases more energy than humanity has used throughout its entire history. The sun has been doing this for 4.5 billion years and will continue for roughly another 5 billion. Stars are the powerhouses of the universe. They convert matter into energy through nuclear fusion, releasing the binding energy that holds atomic nuclei together. A single gram of hydrogen fully fused into helium releases about 630 billion joules. That's equivalent to burning roughly 20,000 gallons of gasoline. But even stars are modest compared to the truly extreme objects in the cosmos. Supermassive black holes at the centers of galaxies can outshine their entire host galaxies when they're actively feeding. Quasars, powered by such black holes, can emit the energy of 1 trillion suns. Gamma-ray bursts, the explosive deaths of massive stars, release more energy in seconds than our sun will produce in its entire lifetime. The universe is awash in energy. The challenge is harnessing it. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification system for civilizations based on their energy consumption. This Kardashev scale has become a staple of discussions about advanced civilizations and their capabilities. A Type 1 civilization can harness all the energy available on its home planet. This includes solar energy falling on the planet, geothermal energy from the planet's interior, wind, tides, and any other planetary energy source. Kardashev estimated this at roughly 4 times 10 to the 16 watts for an Earth-like planet. Humanity isn't there yet. Current estimates place us at roughly Type 0.7 on the scale. We use only a tiny fraction of the energy available on Earth. Most sunlight falls on deserts, oceans, and wilderness without being captured. Most geothermal energy remains untapped. We're still climbing toward Type 1. A Type 2 civilization can harness all the energy of its home star. This is an almost inconceivable step up. For our sun, that would mean capturing all 3.8 times 10 to the 26th watts of output. Every photon, every particle of solar wind, nothing wasted. The classic concept for achieving Type II status is the Dyson sphere, proposed by physicist Freeman Dyson in 1960. This would be a megastructure surrounding a star, capturing all its radiation. It might be a solid shell, though that's structurally problematic, or, more likely, a swarm of orbiting collectors, sometimes called a Dyson swarm. Building a Dyson swarm would require dismantling planets for raw materials. Mercury, with its dense metallic composition and proximity to the Sun, is often suggested as a starting point. The engineering challenges are staggering, but nothing about a Dyson swarm violates known physics. Given sufficient technology and time, it's theoretically achievable. A Type III civilization harnesses all the energy of its home galaxy, every star, every black hole, every source of power across hundreds of billions of stellar systems. This would require spreading across the entire galaxy, building Dyson swarms around countless stars, operating on timescales and distances that dwarf anything we've discussed. Some scientists have proposed even higher levels. Type IV civilizations might harness energy on the scale of galaxy clusters or superclusters. Type V might somehow tap into the energy of the entire observable universe. These concepts become increasingly speculative and may not even be meaningful. Now, where does intergalactic travel fit on this scale? The energy required to accelerate a spacecraft to relativistic velocities depends on its mass and target speed. We can calculate this using Einstein's famous equation relating mass, velocity, and kinetic energy at relativistic speeds. Let's consider a modest spacecraft. Say, 1 million kilograms, roughly the mass of a fully loaded jumbo jet, not a generation ship, not a self-sustaining colony, just a basic vehicle that might carry a small crew and some supplies. To accelerate this spacecraft to 50% the speed of light would require approximately 1.4 times 10 to the 22nd joules of energy. That's about 24 times the total annual energy consumption of human civilization, just for the acceleration phase. You'd need roughly the same again to slow down at your destination. To reach 90% light speed, the energy requirement jumps to about 3.2 times 10 to the 23rd joules. That's over 500 times humanity's annual energy consumption for a single spacecraft, carrying 1 million kilograms, barely enough for a meaningful mission. Now consider what you'd actually need for an intergalactic voyage. Not 1 million kilograms, but perhaps billions of kilograms. A self-sustaining habitat capable of supporting a population for millions of years, manufacturing facilities, repair systems, agricultural or synthetic food production, backup systems for every critical function. The energy requirements multiply accordingly. We're talking about harnessing the output of entire stars, perhaps multiple stars, just to launch a single mission. This is why many scientists consider intergalactic travel to be the domain of Type II or Type III civilizations at minimum. We would need to increase our energy production by factors of millions before such missions became remotely feasible. Even then, they would represent enormous investments of resources. But here's an interesting question. Where would the energy come from? For interstellar missions within our galaxy, solar power remains an option, at least for the acceleration phase. Giant lasers powered by solar collectors could push light sails to significant fractions of light speed. This is the concept behind Breakthrough Starshot. It requires enormous infrastructure but uses energy that's freely available from our Sun. For intergalactic missions, the calculus is different. You can't beam power to a spacecraft that's millions of light years away. The beam would spread out and become useless long before reaching its target. The spacecraft would need to carry its energy source with it. We've already discussed antimatter as the most energy-dense fuel known. In principle, you could store enough antimatter to power an intergalactic voyage. In practice, we can't produce or store antimatter anywhere near the quantities needed. What about nuclear fusion? Our Sun runs on fusion, converting hydrogen into helium. If we could master controlled fusion, we'd have access to an almost unlimited energy source. The hydrogen in Earth's oceans alone could power our civilization for billions of years. But fusion is hard. Despite decades of research and billions of dollars invested, we still haven't achieved sustained fusion energy production. The ITER project in France aims to demonstrate fusion power by 2035. Even if successful, practical fusion power plants are probably decades further out. And even fusion has limits. The efficiency of converting mass to energy through fusion is less than 1%. While vastly better than chemical fuels, it's still not enough for relativistic travel with reasonable fuel masses. Some theorists have proposed even more exotic energy sources. What about extracting energy from black holes? When matter falls into a black hole, it can release tremendous energy before crossing the event horizon. The accretion disks around active black holes are the most luminous objects in the universe precisely because of this process. In theory, a sufficiently advanced civilization might engineer artificial accretion to generate power. Even more speculatively, rotating black holes contain enormous amounts of rotational energy that might somehow be extracted. The physicist Roger Penrose proposed a theoretical mechanism for this in 1971. Objects thrown into the ergosphere of a rotating black hole could emerge with more energy than they entered with, slowly draining the black hole's spin. Could a civilization harness this process for propulsion? The physics doesn't forbid it, but the engineering challenges are almost literally astronomical. You'd need to manipulate matter near a black hole without falling in yourself. You'd need to somehow convert the extracted energy into thrust. The difficulties compound almost beyond imagination. What about vacuum energy? Quantum mechanics tells us that empty space isn't really empty. Even in a perfect vacuum, virtual particles constantly pop into existence and annihilate each other. This quantum foam contains energy, potentially enormous amounts of it. Some calculations suggest that a cubic meter of empty space contains more energy than all the matter in the observable universe. If we could somehow tap this zero-point energy, we'd have essentially unlimited power, but there's a problem. While vacuum energy is real and has been experimentally confirmed through effects like the Casimir force, we don't know how to extract useful work from it. The energy is locked in the quantum vacuum state. It might be fundamentally inaccessible, a cosmic background that exists but cannot be harnessed. Many physicists are skeptical that vacuum energy will ever provide a practical power source, but our understanding of quantum mechanics and general relativity remains incomplete. Perhaps some future theory will reveal possibilities we can't currently imagine. This brings us back to a theme we've touched on before. The limitations we face aren't necessarily permanent. Our ancestors couldn't have imagined nuclear power, smartphones, or genetic engineering. Our descendants might develop energy technologies that would seem like magic to us, but we must also remain humble about the difference between possible and practical. Many things are physically possible yet may never be achieved. It's physically possible to count every grain of sand on Earth, but nobody will ever do it. Some theoretically achievable feats require resources or time beyond any civilization's reach. Intergalactic travel might fall into this category. Perhaps no civilization ever develops the energy technology required. Perhaps the universe is effectively divided into isolated islands, each galaxy a separate domain that never interacts with its neighbors. Or perhaps not. Perhaps somewhere in the cosmos, a civilization has solved these problems. Perhaps they've harnessed the power of stars, or black holes, or vacuum energy, and are now spreading between galaxies. Perhaps they passed through our neighborhood millions of years ago, found nothing interesting, and moved on. This is one possible resolution to the Fermi paradox. Intelligent life might be common but confined. Each civilization might be trapped in its home galaxy by the same barriers we're discovering. The apparent silence of the universe might reflect not absence of life, but the physical impossibility of contact. Alternatively, the energy barriers might filter for a certain type of civilization. Perhaps only those species that learn to cooperate on massive scales, pooling resources across entire solar systems, can generate the energy needed for intergalactic travel. Perhaps aggression and competition, traits that might help civilizations survive early challenges, ultimately prevent them from reaching the energy levels required for cosmic expansion. In this view, the universe might be a test. Only those civilizations that achieve profound unity and long-term thinking can pass beyond their galactic cradles. The rest remain isolated, perhaps forever. This is speculation, of course. We have exactly one data point about civilizations ourselves, and we haven't even left our own solar system yet. Drawing cosmic conclusions from such limited evidence is risky, but pondering these possibilities serves a purpose. It reminds us that the challenges we face aren't just technical. They're also social, political, and philosophical. How we organize ourselves, how we cooperate or compete, how we balance short-term needs against long-term goals, these factors may ultimately determine whether humanity ever reaches beyond the Milky Way. Let me offer one more perspective on energy before we move on. The total energy content of the observable universe is staggering. If you add up all the mass energy of stars, gas, dark matter, and dark energy, you get roughly 4 times 10 to the 69th joules. That's a 4 followed by 69 zeros. This energy exists, it's out there. The universe is not energy poor. It's energy rich beyond imagination. The challenge is access. Most of this energy is locked in forms we can't use, in places we can't reach, on timescales we can't bridge. It's like dying of thirst while floating in the ocean. The resource surrounds you but remains unavailable. Perhaps this is a fundamental feature of existence. Perhaps resource abundance always comes with access limitations. Perhaps every civilization faces this paradox. Surrounded by energy, they can sense but cannot grasp. Or perhaps it's a challenge waiting to be overcome. Perhaps the universe contains energy precisely because it's meant to be used. Perhaps civilizations are the universe's way of liberating that energy, of transforming potential into action, of bringing the cosmos to life. This is a beautiful thought, even if it might be wishful thinking. The idea that we matter, that our struggles have cosmic significance, that we're part of something larger than ourselves. It's the kind of meaning that makes existence worthwhile, regardless of whether we ever cross the gulf to Andromeda. Now let's explore another dimension of our confinement. Let's talk about the dark matter and dark energy that dominate our universe, and how these mysterious substances shape the cosmic landscape we're trying to navigate. We've talked about the visible universe, the stars and galaxies and nebulae that light up our telescopes, the planets and moons we dream of exploring, the vast distances measured in light years. But here's something that should stop you in your tracks. Everything we can see, everything made of atoms, everything that emits or absorbs light, accounts for less than 5% of the universe's total content. Let that sink in for a moment. The entire visible cosmos, from the smallest dust grain to the largest galaxy cluster, is a tiny minority of what exists. The rest is dark, invisible, mysterious, and it shapes everything. Dark matter makes up roughly 27% of the universe. Dark energy accounts for approximately 68%. Together, these invisible components dominate cosmic evolution. They determine how galaxies form, how they move, and ultimately, whether we can ever travel between them. Let's start with dark matter. The story begins in the 1930s with Swiss astronomer Fritz Zwicky. He was studying the Coma Cluster, a massive collection of over 1,000 galaxies about 320 million light-years away. By measuring how fast the galaxies within the cluster were moving, Zwicky could estimate the cluster's total mass using gravitational physics. The galaxies were moving fast, too fast. Based on their velocities, they should have flown apart long ago. The visible mass of the cluster, the stars and gas he could see, wasn't nearly enough to hold them together. Zwicky proposed that some invisible matter must be providing additional gravitational attraction. He called it Dunkle Materie, German for dark matter. At the time, most astronomers dismissed his idea as a measurement error. Decades later, American astronomer Vera Rubin found similar evidence within individual galaxies. In the 1970s, she measured the rotation speeds of spiral galaxies. According to Newton's laws, stars at the outer edges of galaxies should move more slowly than stars near the center, just as outer planets in our solar system orbit more slowly than inner ones. But Rubin found something strange. The outer stars were moving just as fast as the inner ones. The rotation curves were flat, not declining. Something was wrong with our understanding. Either Newton's laws failed at galactic scales, or there was invisible matter extending far beyond the visible stars, providing gravitational pull that kept the outer regions spinning rapidly. Most physicists concluded that dark matter was real. The evidence has only grown stronger since then. Gravitational lensing, the bending of light by massive objects, reveals dark matter's presence. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that can only be explained if dark matter existed in the early universe. Computer simulations of cosmic structure formation require dark matter to produce anything resembling the observed universe, yet we still don't know what dark matter actually is. It doesn't emit light. It doesn't absorb light. It passes through ordinary matter like a ghost. The only way we detect it is through its gravitational effects. Physicists have proposed numerous candidates. Weakly interacting massive particles, called WIMPs, were long the leading contenders. These hypothetical particles would interact through gravity and the weak nuclear force, but not through electromagnetism or the strong force. Experiments deep underground, shielded from cosmic rays, have searched for WIMPs for decades without success. Axions are another possibility. These extremely light particles were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. They would be produced in enormous quantities in the early universe and would behave like dark matter. Specialized experiments are now searching for axion signatures. Some theorists have proposed primordial black holes formed in the very early universe before stars existed. These could have a wide range of masses and would be virtually invisible except through their gravity. Recent gravitational wave observations have constrained but not eliminated this possibility. Others have questioned whether dark matter exists at all. Modified gravity theories, like modified Newtonian dynamics or MOND, propose that our understanding of gravity is incomplete. Perhaps gravity behaves differently at large scales, eliminating the need for invisible matter. Most physicists remain skeptical of modified gravity because it struggles to explain all the evidence that dark matter explains so well. But the debate continues. Science works by constantly questioning its assumptions. For our purposes, what matters is this: dark matter shapes the cosmic web. When we map the distribution of galaxies across the universe, we find they're not scattered randomly. They form a vast network of filaments and walls surrounding enormous empty voids. This cosmic web stretches across billions of light-years, the largest structure in existence. Dark matter created this web. In the early universe, tiny density fluctuations in the dark matter distribution grew over time through gravitational attraction. Regions slightly denser than average pulled in more matter, becoming denser still. Regions slightly underdense lost matter, becoming emptier. Over billions of years, this process sculpted the cosmic web we observe today. Ordinary matter, the stuff that makes stars and planets, fell into the gravitational wells carved by dark matter. Galaxies formed where dark matter concentrated. the voids between them grew ever emptier. This means our Milky Way exists because of dark matter, the gravitational scaffolding that allowed our galaxy to form, the structure that holds it together, the very ground beneath our cosmic feet, all of it shaped by matter we cannot see. Now consider what this means for intergalactic travel. Any voyage beyond the Milky Way would traverse regions shaped by dark matter. The distribution of matter between galaxies, the gravitational landscape affecting trajectories, the very structure of the local group, all are consequences of dark matter dynamics. We can map this structure through its gravitational effects. We can predict how objects will move through it, but we can't interact with dark matter directly. We can't use it for propulsion, shielding, or any practical purpose. It's there, influencing everything, yet completely beyond our manipulation. Some speculative ideas propose that advanced civilizations might find ways to harness dark matter. If dark matter particles can interact through the weak force, perhaps future technology could capture and utilize them somehow, but this remains pure speculation, far beyond any foreseeable capability. Dark matter is the unseen architect of cosmic structure. We live in the house it built without being able to touch its walls. Now let's turn to something even stranger, dark energy. If dark matter is mysterious, dark energy is positively baffling. We understand dark matter's role even if we don't know what it is. Dark energy challenges our fundamental understanding of physics. The story begins with those supernova observations in 1998 that I mentioned earlier. Two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were trying to measure the deceleration of cosmic expansion. Everyone expected expansion to be slowing down. Gravity pulls things together. The mutual attraction of all the matter in the universe should be acting like brakes, gradually reducing the expansion rate. The question was how quickly it was slowing. But the supernovae told a different story. Distant supernovae were fainter than expected. They were farther away than they should have been if expansion were decelerating. The universe wasn't slowing down, it was speeding up. This discovery earned the team's leaders the Nobel Prize in Physics in 2011. It also threw cosmology into upheaval. What could cause the universe to accelerate against the pull of gravity? Something must be pushing it apart, something stronger than all the gravitational attraction of all the matter in existence. Scientists named this mysterious force dark energy. Like dark matter, the name reflects our ignorance. We call it dark because we can't see it, can't detect it directly, don't really know what it is. The simplest explanation is that dark energy is a property of empty space itself. Einstein's equations of general relativity actually include a term called the cosmological constant that could produce exactly this effect. Einstein originally included this term to create a static universe, then removed it after Hubble discovered cosmic expansion, calling it his greatest blunder. Perhaps Einstein was right the first time, just for the wrong reasons. The cosmological constant might be real, representing some intrinsic energy of the vacuum. As the universe expands and creates more space, it creates more vacuum energy, which drives further expansion, creating even more space. It's a runaway process that accelerates over time. This explanation fits the observations well, but raises profound questions. If vacuum energy is real, quantum mechanics predicts it should be enormously larger than what we observe. The calculated value exceeds the observed value by roughly 120 orders of magnitude. This is perhaps the worst prediction in the history of physics. Something is terribly wrong with our understanding. Either quantum mechanics is dramatically flawed in ways we don't comprehend, or some unknown mechanism cancels almost all of the predicted vacuum energy, leaving just a tiny residue. Neither option is satisfying. Other explanations for dark energy exist. Perhaps it's not a constant at all, but a dynamic field, that varies across space and time. Such proposals go by names like quintessence or phantom energy. Perhaps our theory of gravity is incomplete and the acceleration is an artifact of unknown physics rather than a real force. We simply don't know. Dark energy is one of the deepest mysteries in modern science. What we do know is what it does. Dark energy pushes the universe apart. And because it's a property of space itself, its effect grows as space expands. More space means more dark energy, means faster expansion, means more space. The acceleration feeds itself. Early in the universe's history, matter dominated. Galaxies were closer together and gravity was stronger than dark energy. The expansion actually was slowing down during this era. But as the universe expanded, matter became more dilute, while dark energy remained constant. Eventually, about 5 billion years ago, dark energy became dominant. Expansion began accelerating. It's been accelerating ever since. The consequences for intergalactic travel are devastating. Right now, the Andromeda Galaxy is approaching us. Local gravity overwhelms cosmic expansion at these relatively small distances. Our local group of galaxies is gravitationally bound and will remain so, but beyond the local group, dark energy rules. Distant galaxies are receding from us faster and faster, and the expansion rate itself is increasing. Current models suggest that in roughly 100 billion years, all galaxies beyond our local group will have passed beyond the observable universe. The light they emit will never reach us. Future astronomers will see only darkness beyond a merged Milky Way Andromeda galaxy. This is called the Big Freeze scenario. The universe will continue expanding forever, growing colder and emptier. Stars will burn out. Black holes will evaporate through Hawking radiation over timescales so long they make our current discussion seem like a blink. Eventually, the universe will approach absolute zero, a dark, diffuse sea of particles drifting ever farther apart. It's a sobering vision. The ultimate fate of cosmic expansion isn't a glorious culmination, but a long, cold slide toward maximum entropy. But dark energy's effects appear long before this final fate. They're already shaping the universe we inhabit. Consider the cosmic event horizon I mentioned earlier. Beyond a certain distance, objects are receding from us faster than light. Light they emit today will never reach us. They've passed beyond our cosmic horizon, lost to us forever. This horizon isn't static. As expansion accelerates, it's effectively shrinking. More and more of the universe is passing beyond our reach. If we wanted to send probes to distant galaxies, we'd need to launch them soon, in cosmic terms. Wait too long, and our targets will have receded beyond any possibility of reaching them, even traveling at light speed. Of course, soon in cosmic terms still means billions of years. We have time, but not infinite time. The window of cosmic accessibility is gradually closing. Some researchers have calculated which galaxies we could theoretically reach if we developed sufficiently advanced technology. The answer depends on assumptions about acceleration profiles, travel speeds, and how dark energy evolves over time. Under optimistic assumptions, perhaps we could reach galaxies as far as the Virgo cluster, about 50 million light-years away, before dark energy carries them beyond reach. Under pessimistic assumptions, we might be limited to just the local group. Either way, the vast majority of the observable universe is already beyond our grasp. The 2 trillion galaxies we can see are like photographs of places we can never visit, postcards from an inaccessible realm. This limitation has a philosophical dimension that's worth exploring. Throughout human history, we've generally assumed that the universe is knowable, that with enough effort and ingenuity we could eventually understand everything, that no region of existence is fundamentally off limits. Dark energy challenges this assumption. It suggests that most of the cosmos is not just currently inaccessible but permanently inaccessible, No amount of technological progress will ever allow us to visit galaxies beyond a certain distance. The physics forbids it. We're confined not by our limitations, but by the structure of reality itself. Some find this disturbing. It seems to mock our ambitions, to place arbitrary barriers around our aspirations. The universe tantalizingly shows us wonders we can never touch. Others find a different meaning. Perhaps the limitation is actually a gift. Perhaps being shown a universe larger than we can ever explore inspires humility, wonder, and a deeper appreciation for what we do have access to. The local group, our cosmic neighborhood, contains over 80 galaxies, trillions of stars, countless worlds, wonders beyond anything we've discovered so far. Even if we never leave this gravitationally bound cluster, we have an enormous realm to explore. Perhaps that's enough. Perhaps the vastness beyond is meant to be admired, not possessed. Perhaps beauty doesn't require accessibility. These are not scientific questions, they're philosophical and perhaps spiritual reflections. But science often leads us to such reflections. The deepest discoveries about the universe frequently become discoveries about ourselves. Dark matter and dark energy represent the limits of our current understanding. They remind us that the cosmos is stranger than we imagined, governed by forces we barely comprehend. They humble us while simultaneously inspiring us to learn more. Perhaps someday we'll understand what dark matter is made of. Perhaps we'll unravel the mystery of dark energy. Perhaps our descendants will manipulate these invisible components as easily as we manipulate electromagnetism today. Or perhaps some mysteries are permanent. Perhaps reality has layers that will forever remain hidden. Perhaps knowing everything isn't the point. What matters is the search, the questions. The journey of discovery that's taken us from campfires to telescopes peering at the edge of the observable universe. The human adventure of trying to understand our place in the cosmos. That adventure continues regardless of whether we ever physically leave our galaxy. In a sense, our minds have already traveled to the most distant reaches of existence. We've touched black holes and quantum particles, and the first moments after the Big Bang with our understanding. We've mapped the cosmic web and measured the expansion of space and detected gravitational waves from colliding neutron stars. The universe is our home, whether or not we can visit all of it. Now let's turn to something that might offer hope amidst these cosmic limitations. Let's explore the possibility that we might not need to physically travel between galaxies at all. Let's talk about alternative forms of cosmic connection and presence. What if we've been thinking about this problem the wrong way? Throughout this entire exploration, we've focused on physically moving matter across intergalactic distances, sending ships, probes, people, or machines from one galaxy to another. We've calculated the energy requirements, contemplated the timescales, wrestled with the physics limitations. But physical travel isn't the only way to be present somewhere. It isn't even the only way to explore or connect. Consider how you're experiencing these ideas right now. You're not physically in my presence. You might be thousands of miles away from where these words were created. Yet somehow my thoughts are entering your mind. Patterns of information are crossing the distance between us, carried by light, by electrical signals, by the magic of technology. In a very real sense, I'm present with you right now. Not my body, but something perhaps more essential, my ideas, my perspective, the patterns that make communication meaningful. This suggests an alternative approach to cosmic exploration. What if, instead of sending matter, we focused on sending information? Information can travel at the speed of light. Pure electromagnetic signals, unencumbered by mass, zip across the cosmos at the universal speed limit. A radio transmission or laser pulse sent toward Andromeda would arrive in 2.5 million years, still an enormous duration but achievable without exotic physics or impossible energy requirements. We're already doing this, in a modest way. Every television broadcast, every radar pulse, every cell phone call sends radio waves outward into space. These signals don't stop at the edge of our atmosphere. They continue traveling, spreading out in an ever-expanding sphere centered on Earth. The earliest radio broadcasts from the 1920s have now traveled roughly 100 light-years from Earth. They've washed over hundreds of star systems, carrying fragments of music, voices, and static. Any sufficiently advanced civilization within that bubble might have detected our presence. Of course, these accidental transmissions are weak and garbled. They weren't designed for interstellar communication, but they demonstrate the principle. Information can escape our planet and travel to the stars. Intentional transmissions could go much further and say much more. In 1974, astronomers used the Arecibo radio telescope in Puerto Rico to send a carefully crafted message toward the globular cluster Messier 13. This cluster contains hundreds of thousands of stars packed into a sphere about 145 light-years across. The message, designed by Frank Drake and Carl Sagan among others, contained information about our numeral system, the elements of life, the structure of DNA, a representation of a human being, and a diagram of our solar system. The message will take about 25,000 years to reach its destination. If anyone receives it and replies immediately, the response will arrive in another 25,000 years. We're talking 50,000 years for a single exchange. But the message exists. It's out there right now, a tiny whisper of human presence spreading through the Milky Way. More ambitious projects have sent physical artifacts. The Voyager Golden Records attached to both Voyager spacecraft contain images, sounds, music, and greetings in 55 languages. They include instructions for playing the record and diagrams showing our location relative to nearby pulsars. These records are currently traveling beyond our solar system at about 17 kilometers per second. At that speed, they would take roughly 75,000 years to reach the nearest star system if they were heading in that direction, which they're not. The golden records are more symbolic than practical. Their real audience might be us, not hypothetical extraterrestrials. They remind us of our curiosity, our hope, our desire to connect with something beyond ourselves. But what if we got serious about interstellar communication? What if we built dedicated transmitters designed to send messages across the galaxy? The technology exists, at least in principle. Powerful lasers could send tightly focused beams to specific star systems. These beams would remain coherent over interstellar distances much better than radio waves. A civilization looking in our direction at the right time might detect the pulse. The SETI Institute and other organizations have debated whether we should attempt such active messaging. Some scientists worry about the risks of announcing our presence to unknown civilizations. Others argue that any civilization capable of reaching us would likely have detected our existence already through our radio leakage. This debate, sometimes called METI for messaging to extraterrestrial intelligence, remains unresolved, but it highlights an important point. We have the capability to send messages to the stars. We're already doing it, whether we intend to or not. Could we extend this capability to intergalactic distances? In principle, yes. A sufficiently powerful transmitter could send signals to Andromeda. The challenge is ensuring the signal remains detectable after crossing 2.5 million light-years. Radio waves and laser beams spread out as they travel. The inverse square law applies mercilessly. Double the distance and the signal strength drops to 1/4. Across intergalactic distances, the spreading is enormous. To compensate, you'd need either incredibly powerful transmitters or incredibly sensitive receivers, or both. Consider a scenario where humanity builds a network of transmitters powered by orbital solar collectors. These transmitters could generate beams far more powerful than anything currently possible. Aimed at Andromeda, they might remain detectable across the void. The message would take 2.5 million years to arrive. Any response would take equally long. You're not having a conversation, you're making a statement, sending a cosmic message in a bottle that might or might not find a recipient. But even one-way communication could be meaningful. You could transmit the entirety of human knowledge, every book, every scientific paper, every work of art. You could send genetic information, the blueprints for human biology. You could encode everything that makes us who we are. If another civilization received and understood this transmission, they would know us, not physically but intellectually. Our thoughts, our achievements, our dreams would exist in their minds. We would have achieved a form of immortality through information. Some philosophers argue this is actually more significant than physical presence. Bodies are temporary, they age, decay, and die. But ideas can persist indefinitely. The thoughts of Socrates still influence us 2,400 years after his death. His body is long gone, but his intellectual presence remains. Perhaps this is the true form of intergalactic travel, not ships carrying fragile biological organisms, but transmissions carrying the essence of who we are. Not physical exploration, but intellectual expansion. There's something beautiful in this vision, and something sad. Beautiful because it offers a way to transcend our limitations, to extend our presence beyond the reach of any physical vehicle, to participate in the cosmic conversation even if we can never attend in person. Sad because it means accepting that we will never truly go there ourselves, never feel the light of an alien sun on our faces, never walk on worlds in another galaxy, never experience firsthand the wonders that might await. But perhaps this sadness is misplaced. Perhaps we're too attached to physical presence as the measure of reality. Think about your own life. The people who have influenced you most profoundly may include many you've never met. Authors who died centuries ago. Scientists whose work you've studied. Artists whose creations moved you. These individuals are present in your life through their ideas, not their bodies. In a sense, they've traveled to you across time. Their thoughts have crossed centuries to enter your mind. This is a form of time travel through information. Similarly, we might travel to distant galaxies through information, not matter. Our descendants, millions of years hence, might receive transmissions from civilizations in Andromeda, absorbing alien thoughts, alien art, alien science, and they might send our own accumulated wisdom in return. This would be a slow conversation, spanning millions of years. But it would be a real connection, a genuine sharing of minds across the cosmic void. Some researchers have explored even more radical possibilities. What if we could transmit not just information about ourselves, but ourselves as information? This brings us back to the concept of mind uploading. If consciousness is fundamentally a pattern of information, and if that pattern could be captured and encoded, it might be transmittable. You could beam yourself to another galaxy. At the receiving end, assuming someone was there to receive, the pattern could be reconstructed. In a new substrate, biological or artificial, a version of you would exist in Andromeda. It would have your memories, your personality, your sense of identity. It would experience arrival in another galaxy. The original you would remain on Earth, of course. You wouldn't experience the journey or the arrival. You'd be sitting at home while your copy had adventures across the cosmos. Is that really travel? Or is it just making a copy in a distant location? This is the teleportation problem that philosophers love to debate. If you're disassembled here and reassembled there, is the new version really you? Does continuity of consciousness require continuity of physical substrate? We don't know. We don't even have a scientific theory of consciousness that could answer such questions. They remain open, perhaps forever. But let's imagine these philosophical puzzles could be resolved or simply accepted. Let's imagine we transmitted human minds to Andromeda, and they were successfully received and embodied. Those beings would be us in some meaningful sense. They would carry our heritage, our values, our way of seeing the universe. Through them, humanity would have reached another galaxy. They would also be something new. Separated by 2.5 million years from their origin, shaped by experiences we can't imagine, evolved in directions we can't predict, they would become their own civilization, perhaps forgetting Earth entirely over the eons. Is this colonization? Is it reproduction? Is it a form of cosmic seeding, spreading the spark of human consciousness across the universe? Perhaps all of these, perhaps something we don't have words for yet. There's another form of cosmic connection worth considering. We're already linked to the wider universe in ways that don't require travel at all. You are made of atoms forged in stars. The hydrogen in your body was created in the Big Bang itself, nearly 14 billion years ago. The carbon, nitrogen, and oxygen were synthesized in the cores of massive stars that exploded billions of years before Earth formed. The iron in your blood, the calcium in your bones, the phosphorus in your DNA all came from stellar nucleosynthesis. You are stardust. This isn't poetry, it's literal truth. Those stars that contributed to your body were themselves made of material from even earlier generations of stars. The cosmos has been recycling atoms for billions of years. The particles in your body have been part of countless other structures, other worlds, other beings. In a very real sense, you have already traveled the galaxy. The atoms that compose you have. They've been through stellar furnaces, drifted through interstellar clouds, accumulated into planets, participated in unknown processes on unknown worlds. They carry a history stretching back to the beginning of time. This perspective offers a different kind of cosmic connection. We're not separate from the universe, looking at it from outside. We're part of it, woven into its fabric, participating in its story. The same physics that operates in Andromeda operates in every cell of your body. The same fundamental forces shape distant galaxies and your own thoughts. We are the universe becoming conscious of itself. Through us, the cosmos explores its own nature, contemplates its own existence, asks its own questions. This sounds mystical, but it emerges directly from scientific understanding. Consciousness exists. We exist. We're made of cosmic material, governed by cosmic laws. There's nothing supernatural about recognizing our deep connection to everything that exists. Carl Sagan expressed this beautifully when he said, "We are a way for the cosmos to know itself. The atoms that compose us have merely been rearranged. The universe hasn't created consciousness from nothing. It has organized itself into patterns capable of self-reflection." When you wonder about distant galaxies, you're the universe wondering about itself. When you feel awe at the cosmic scale, the cosmos is experiencing awe at its own grandeur. We're not observers standing outside reality. We're reality observing itself. From this perspective, the question of whether we can leave the Milky Way takes on new meaning. In a sense, we already encompass the entire universe because we're made of it. The barrier between ourselves and Andromeda is less solid than it appears. Of course, this philosophical perspective doesn't solve the practical challenges of physical travel. You still can't visit Andromeda in any bodily sense. The engineering problems remain unsolved. But it might help us find peace with our limitations. If we're already connected to everything, already participants in the cosmic story, the inability to physically travel everywhere becomes less tragic. We're home everywhere because everywhere is made of the same stuff we are. This brings me to something profound about the human condition. We're creatures of both infinite aspiration and finite capability. We can imagine traveling to the edge of the observable universe even though we can barely leave our own planet. We can conceive of eternity even though our lives are measured in decades. This tension between imagination and limitation defines us. It drives our science, our art, our philosophy. It makes us reach beyond our grasp, strive for the impossible, dream of the unreachable. Perhaps that's the point. Perhaps the value isn't in achieving our goals, but in having them. Perhaps the dream of intergalactic travel matters even if the travel itself remains forever impossible. Throughout history, impossible dreams have guided humanity forward. The dream of flying preceded actual flight by millennia. The dream of curing disease preceded modern medicine by centuries. Dreams don't require fulfillment to be meaningful. Maybe the dream of crossing between galaxies will inspire technologies and discoveries we can't anticipate. Maybe the effort to solve these impossible problems will yield solutions to more tractable ones. Maybe the contemplation of cosmic distances will give us perspective on our earthly challenges. Or maybe the dream is valuable in itself, regardless of practical outcomes. Beauty doesn't require utility. Wonder doesn't require application. Sometimes the highest human experiences are their own justification. Gazing at the stars and imagining voyages we can never take might be one of those experiences. The longing for the unreachable infinite might be a core part of what makes us human. Let's explore one more dimension of this question. Let's talk about whether physical intergalactic travel might be happening elsewhere in the cosmos, even if we can't achieve it ourselves. Let's discuss the search for extraterrestrial intelligence and what it might tell us about the possibilities we face. We've spent this entire journey examining why humanity cannot leave the Milky Way. The speed of light barrier, the incomprehensible distances, the energy requirements beyond our wildest capabilities, the expansion of space itself working against us. But here's a question that should haunt us. What if someone else has figured it out? The universe is approximately 13.8 billion years old. Our sun and solar system formed only about 4.6 billion years ago. That means the cosmos was churning out stars and planets for over 9 billion years before Earth even existed. During those billions of years, countless civilizations might have arisen, some on planets circling stars far older than ours, some with millions or even billions of years head start on us. If even one such civilization survived and continued advancing, imagine what they might have achieved. We've gone from stone tools to smartphones in roughly 300,000 years. From the Wright brothers to the International Space Station in barely a century. What might a civilization accomplish in 1 million years of continuous progress? 10 million? 1 billion? The scale of potential advancement is staggering. Technologies we consider impossible might be routine for them. Challenges that defeat our imagination might be solved problems in their textbooks. The barriers confining us might be minor inconveniences they barely remember. This line of reasoning leads to one of the most profound questions in science. If advanced civilizations exist, where are they? Why haven't we detected any sign of their presence? This puzzle is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunch conversation in 1950. The paradox arises from a simple observation. The galaxy is old enough and large enough that intelligent life should have arisen many times. Even with conservative estimates, there should be thousands or millions of civilizations in the Milky Way, and if even a small fraction develop the ability to travel between stars, they should have colonized the entire galaxy by now. The math is compelling. Even traveling at a modest fraction of light speed, a civilization could spread across the Milky Way in just a few million years. That's a blink of an eye compared to the galaxy's age. Once you've colonized one star system, you send ships to nearby systems, establish colonies there, and repeat. Exponential growth handles the rest, yet we see nothing. No alien spacecraft, no megastructures around distant stars, no radio signals from advanced civilizations. The galaxy appears empty, despite every reason to expect it should be teeming with life. Many solutions to the Fermi paradox have been proposed. Each carries implications for intergalactic travel. Perhaps intelligent life is far rarer than we assume. Maybe the evolution of complex life requires an extraordinarily unlikely sequence of events. Maybe most planets are sterilized by cosmic catastrophes before intelligence can arise. Maybe Earth is genuinely unusual, a rare oasis in a mostly lifeless cosmos. If life is rare, that would explain the silence, but it would also mean we might be alone, or nearly so, in a universe vast beyond comprehension. There might be no one to learn from, no one who has solved the problems we face. Every barrier to intergalactic travel might remain permanently unsolved because no one has ever overcome them. Another possibility is that civilizations don't last long enough to colonize the galaxy. Perhaps every intelligent species eventually destroys itself through war, environmental collapse, or technological disaster. Perhaps reaching for the stars requires social and political stability that no species can maintain across the necessary timescales. This is a sobering thought. It suggests that the same intelligence that allows a species to develop technology might also lead to self-destruction. The very qualities that make interstellar travel conceivable might also make survival unlikely. If this is true, intergalactic travel might be a mirage, a destination no civilization ever reaches because none survive long enough. The universe might be littered with the ruins of ambitious species that burned brightly and then vanished, never escaping their home worlds. But perhaps there's a more hopeful explanation. Perhaps advanced civilizations exist but simply don't expand aggressively. Maybe they've chosen to stay home, content with their own solar systems. Maybe the drive to colonize everything is a primitive impulse that mature species outgrow. Some futurists call this the transcension hypothesis. Rather than expanding outward into space, advanced civilizations might turn inward, creating ever more complex virtual realities or exploring inner space at the quantum level. The ultimate technology might be not starships, but mind enhancement, not physical expansion, but mental transcendence. If transcension is the typical path, galaxies might be full of advanced civilizations we simply cannot detect. They would be invisible to us, operating at scales or in dimensions we don't know how to observe. They might have solved every problem we've discussed but have no interest in physical travel anymore. This possibility carries mixed implications. On one hand, it suggests the barriers we face might have solutions. Someone, somewhere, might have figured out how to generate antimatter in bulk or stabilize wormholes or harness dark energy. The physics might permit what we consider impossible. On the other hand, those solutions might lead away from physical exploration rather than toward it. The ultimate answer to intergalactic travel might be that it's possible but pointless, that advanced beings find better things to do with their capabilities than crossing voids between galaxies. There's another intriguing possibility. Perhaps the reason we see no evidence of intergalactic travelers is precisely because such travel is impossible. Perhaps every civilization, no matter how advanced, eventually reaches the same barriers we've discussed: the speed of light, the energy requirements, the expansion of space. Perhaps these are truly fundamental limits that no amount of technology can overcome. In this scenario, the universe would be divided into isolated islands. Each galaxy a separate pocket of life and intelligence, forever cut off from all the others. Civilizations might flourish independently in Andromeda, in the Triangulum galaxy, in countless others across the observable universe. But they would never meet, never exchange ideas, never even confirm each other's existence. This is the cosmic isolation hypothesis. It's perhaps the most melancholy solution to the Fermi paradox. We're not alone in the universe, but we might as well be. Everyone else is just as trapped as we are. How would we ever test these possibilities? How could we know whether intergalactic travel is achieved by others, even if we can't achieve it ourselves? The search for extraterrestrial intelligence, known as SETI, has been ongoing for decades. Radio telescopes scan the skies for signals that might indicate artificial origin. Optical telescopes look for laser pulses or other technological signatures. So far, nothing conclusive has been found. But SETI has largely focused on detecting civilizations within our own galaxy. Looking for signals from other galaxies is far more challenging. The distances are so much greater that any signal would be proportionally fainter. Still, some searches have looked for signs of extremely advanced civilizations in other galaxies. Kardashev Type 3 civilizations, which harness the energy of entire galaxies, should be detectable across cosmological distances. Their waste heat would warm their host galaxies, changing the infrared signature in measurable ways. In 2015, a project called Glimpsing Heat from Alien Technologies, or GHAT, examined 100,000 galaxies for such signatures. They found no obvious candidates. Most galaxies showed normal thermal profiles consistent with natural stellar populations. This doesn't prove advanced civilizations don't exist. Perhaps they're better at managing waste heat than we assume. Perhaps they operate in ways we haven't imagined, but it does suggest that galaxy-spanning mega-civilizations aren't common. If they exist, they're subtle. Some researchers have proposed looking for engineering projects on cosmic scales. Megastructures like Dyson swarms should dim their host stars in distinctive ways. Transit observations, the same technique used to detect exoplanets, might reveal artificial objects passing in front of distant suns. In 2015, astronomers noticed unusual dimming patterns in a star called KIC 8462852, nicknamed Tabby's star. The dimming was irregular and dramatic, unlike anything caused by known natural phenomena. Some speculated it might be evidence of an alien megastructure under construction. Further observations suggested a more mundane explanation, likely dust clouds rather than alien architecture. But the episode demonstrated the kind of evidence that might indicate advanced civilizations. We're learning how to look. More recently, the James Webb Space Telescope has begun studying exoplanet atmospheres in unprecedented detail. It's searching for biosignatures, chemical combinations that might indicate life. While focused on finding any life, not necessarily intelligent life, such discoveries would have profound implications for the Fermi paradox. If life is common but intelligence is rare, we might find many inhabited planets, but no civilizations. If even microbial life is rare, the explanation for cosmic silence would be clear. Either outcome would reshape our understanding of our place in the universe. Let's consider what detecting an intergalactic traveler would actually look like. If a civilization from another galaxy had somehow crossed the void and entered the Milky Way, how would we know? What evidence would they leave? One possibility is direct detection. A spacecraft or probe from another galaxy might be large enough to spot with telescopes. It might emit radiation, reflect sunlight, or occult background stars. If it were actively exploring, it might send signals we could intercept. Remember Oumuamua, the first confirmed interstellar object detected passing through our solar system? When it was discovered in 2017, some scientists briefly wondered if it might be artificial. Its elongated shape and unusual motion sparked speculation about alien probes. Further analysis suggested Oumuamua was probably natural, a fragment of a larger body from another star system. But the excitement revealed something important. We're now capable of detecting objects passing through our cosmic neighborhood. If an alien probe entered our solar system, we might notice it. Of course, any probe from another galaxy would have traveled for millions of years. It might have launched before humanity existed. Its creators might have evolved into something unrecognizable or gone extinct entirely. Even if we detected such an object, communication with its makers might be impossible. Another possibility is indirect evidence. An intergalactic civilization might have left traces of its passage, mining operations that depleted asteroids in characteristic ways, atmospheric modifications on planets they visited, structures that persisted long after they moved on. Archaeology on Earth has taught us to read the traces of vanished civilizations. Perhaps cosmic archaeology could do the same. Perhaps the evidence of ancient travelers is out there, waiting to be recognized by eyes that know what to look for. Some scientists have proposed searching for what they call lurkers, alien probes that might be hiding in our solar system, observing us without revealing themselves. Such probes could be positioned in stable orbits, perhaps at Lagrange points or in the asteroid belt, watching Earth for millennia. This idea might sound paranoid, but it's not entirely unreasonable. If we could send probes to other star systems, we might well design them to be inconspicuous. We'd want to observe without interfering, at least initially. Why wouldn't other civilizations do the same? The problem is that space is vast. Even our solar system contains enormous volumes to hide in. Finding a small, deliberately concealed object would be extraordinarily difficult. We might be observed right now without having any idea. But let's return to the central question. What does the search for extraterrestrial intelligence tell us about intergalactic travel? The silence of the cosmos could mean many things. Perhaps life is rare, perhaps intelligence is rarer still, perhaps civilizations destroy themselves, perhaps they transcend into forms we cannot detect, or perhaps they're all stuck, just like us, confined to their home galaxies by the same barriers we've been exploring, dreaming of crossing the void while accepting they never will. There's something strangely comforting in this possibility. If the limits we face are truly universal, then we're not failures for being unable to overcome them. We're simply living within the rules that govern everyone. The universe treats all its inhabitants equally, granting the same potential and imposing the same constraints. We would be part of a cosmic community, even if we could never meet its other members. Bound by shared limitations. United by common dreams. Separate and yet somehow connected by the very barriers that divide us. This perspective transforms frustration into solidarity. We might never shake hands with beings from Andromeda, but we might know that they exist, that they wonder about us as we wonder about them, that they gaze at our galaxy across the void and dream of impossible journeys. Perhaps that knowledge, if we ever gain it, would be enough. Perhaps knowing we're not alone would satisfy some deep human need, even without physical contact. Perhaps the universe offers communion without proximity, connection without touch. These are speculative thoughts. We don't know if other civilizations exist. We don't know if the Fermi paradox has a single answer or many. The silence might mean something profound, or it might simply reflect our limited ability to listen. But the speculation matters. It expands our imagination. It prepares us for possibilities we haven't yet encountered. It reminds us that our perspective is narrow, our knowledge incomplete, our assumptions provisional. Whatever awaits us in the search for cosmic companions, the search itself enriches us. It pulls our attention beyond daily concerns toward eternal questions. It connects us to the deepest mysteries of existence. It makes us bigger, even as it reveals how small we are. The hunt for extraterrestrial intelligence isn't just about finding aliens. It's about finding ourselves, understanding our place in the cosmic story, confronting our loneliness and our longing, asking what it would mean to share the universe with others. Whether or not we ever receive an answer, the question transforms us. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How big is the solar system, and why we will never leave it? In this video, we reveal the true, mind-blowing scale of our solar system, from the blazing sun and the orbits of Mercury, Venus, Mars, and much more. See you there.